In this video segment, we're introducing a very important concept in chemistry involving chemical quantities. In other words, how do we measure how much of a chemical substance is present? And when we stop and think about that, we realize how important this ability is. For example, we are all concerned globally about the amount of carbon dioxide that is being produced and transferred to the atmosphere. But how do we measure exactly how much carbon dioxide we're emitting and how much is going into the atmosphere? This chapter is going to introduce us to the methods by which we do that. Notice in Chem 2A, this information is found in Chapter 7. In Chem 22, the information is contained in Chapter 6. So to begin the discussion of chemical quantities, we need to actually be able to get a handle on how we determine the masses of individual elements and their atoms. So we have a concept known as atomic mass of an element. And this material can be reviewed in Chem 2A in Chapter 4, Section 4.5, and in Chem 22 in Chapter 4, Section 4.9. So, atomic mass of an element. We're talking here about the average of the atomic masses of all of the naturally occurring isotopes of an element, weighted according to their abundance in nature. And if you look on the periodic table lists in the box containing the information about each element, not only its atomic number, its number of protons, which we have been introduced to, but there is another number in the box for each element, which is the atomic mass of that element. For example, let's take a look at carbon. If we look at carbon on the periodic table, we see that the atomic mass of carbon to four significant figures is listed as 12.01. And what does that mean? Well, this is an average mass of a carbon atom. No naturally occurring carbon atom actually has this average mass. There are three naturally occurring isotopes of carbon in nature: carbon-12, carbon-13, and carbon-14. In order to get the average atomic mass for carbon, we need to look at these naturally occurring isotopes, consider what their individual masses are, and average those by abundance. So carbon-12 is actually our reference point for measuring the masses of all atoms that we find in nature, all isotopes of atoms. It is assigned a mass of exactly 12 AMUs, linked, of course, to its mass number, number of protons and neutrons. Carbon-13 and carbon-14 would have masses of about 13 and 14 AMUs, respectively. And notice I have been using a unit, atomic mass unit, that I haven't introduced to you. So let me just stop and mention I have here on the board, atomic mass unit. What is that? That is not one of the units that we looked at when we discussed the metric system, because it's time to introduce it now. It is a mass unit that is appropriate for measuring the masses of tiny individual atoms. So it's a very, very small unit of mass used to express masses of individual atoms. So important from a principle statement, but not so useful in the lab because we can't see matter on such a tiny level, and we'll discuss how to address that. Anyway, back to the atomic mass of carbon-12, because 98.9% of all naturally occurring carbon atoms are carbon-12 isotopes, we see that the average atomic mass of carbon is very close to 12 AMUs, the mass of a carbon-12 isotope. So again, the idea is that the atomic masses we see are the average of the isotopes of the element weighted by the abundance of that isotope. Now, how can we use this concept to understand the masses of compounds. We've just spent a chapter looking at how we write chemical formulas for compounds. How would we be able to express the mass of a compound? Well, now we need to introduce the idea of formula mass, which is the sum of the atomic masses of all of the atoms present in the chemical formula of a substance expressed in AMUs. For example, what is the formula mass of iron 3 carbonate? And we just studied how to take the name iron 3 carbonate and write the correct chemical formula for it. So all those nomenclature skills are going to be very important here as we are looking at calculating quantities of chemical substances present. So hopefully you're able to look at this name and very quickly write the correct chemical formula for iron 3 carbonate. Fe2 parentheses carbonate ion CO3 minus 2, right? So Fe2 parentheses CO3 parentheses 3. In other words, 3 carbonate ions is needed to balance the charge on 2 iron 3 ions. So looking at this chemical formula, what does it tell us about the composition of iron 3 carbonate? Well, it tells us that its chemical formula contains 2 iron ions, the Fe2, and that within the carbonate ion formula, there are 3 carbon atoms contained within 3 carbonates and a total of 9 oxygen atoms, 3 times 3, giving us 9 oxygen atoms. So looking at the chemical formula of iron 3 carbonate, we see that it consists of a ratio of 2 iron ions to 3 carbon to 9 oxygen atoms present in the overall formula. And now we're going to take advantage of the atomic masses of iron and carbon and oxygen listed on the periodic table and do some simple multiplication processes. So I see that the atomic mass of iron expressed to 4 significant figures is 55.85 AMUs. I have 2 iron ions I need to account for, so that calculates out 2 times 55.85 to being 111.7 AMUs. Doing similar calculations for 3 carbon times the atomic mass of carbon that we mentioned above, 3 times 12.01 gives us 36.03 AMUs, and 9 oxygens, using the atomic mass of oxygen to 4 significant figures, which is 16. 9 times 16 gives us 144 AMUs contributed by the 9 oxygen atoms in the formula. And totaling these atomic masses up, taking a calculator and doing the calculation here. I'm looking at my calculator, doing the calculation. If you have your calculator out, it's a good time to stop and do the calculation yourself. And I am coming up with 291.7 AMUs, expressing the uncertainty to the 10th place, where uncertainty first begins when we add these values up. So we can state that the formula mass of iron 3 carbonate is 291.7 AMUs.